Hello, I'm John Schiller. I'm back. Professor Hitomi Yamaguchi Greenslit is, as you know, a big shot, and she's on the board of directors of the Society of Manufacturing Engineers, and they're having a board meeting today, so I'm substituting. I'm told you're in chapter 6, right? Somewhere around there. Well, I don't know anything about plastics, so I'm not going to talk about that. But you've already made it through 4 and 5, I hope. Yeah? Those are the toughest ones. Now you'll do 6 sort of as an intermission. I hardly do it when I teach the course. But then the other big chunk, 4 and 5 was a big chunk, the hardest and maybe biggest chunk. The next big chunk is 7 and 8. 7 talks about the technology of metal removal processes. 8 gives a more analytical approach and a more detailed approach. Rather than get into something that will perhaps confuse you because she might approach it a little differently than me, I have carved out the topic of tool materials, which is section 8.3 in the book. So this is a little bit ahead of where you are, but it's something I can do independently without really causing much of a problem to this. And even better, it's something I actually know something about. So I've worked on tests for different tool materials for both industry and otherwise, so we can talk about this. Okay, so if we look at the number of machines, the number of hours spent, the biggest of the different areas of manufacturing. We had the bulk forming, we had the sheet metal, you'll have the welding, you'll have assembly. The biggest one really is metal removal. And so we're cutting material removal, but of course the one we're most concerned about is cutting the metals, removing the metals. Now, when you're cutting something, you need something stronger than what you're cutting in order to do the cutting. So the materials become very important, especially when you're cutting steels and titanium alloys and hardened metals. And even when you're cutting aluminum, you want your cutting tool to last a long time. So what are the requirements that we have for a cutting tool? The first thing is it needs to be high strength. You don't want your tool breaking. The next thing we need is high toughness. And by toughness, we mean impact resistance, that sort of thing. If you think on a lathe or a milling machine, you have oftentimes a tool that's coming around, cutting air, and then all of a sudden hitting metal. It can't fracture, so it has to have a high toughness. So it has to also have a resistance to adhesion, cohesion, and corrosion. Okay? Okay. And usually listed as separate, although it's sort of related because it's related to strength, it has to have high hardness. Okay, so we have to have strength, toughness, resistance to, adhesion, oxidation, corrosion, that sort of resistance, and high hardness. The problem also is, though, these all need to occur at high temperatures usually. When you're cutting metal, it's taking energy. Your machine tool, your lathe, your milling machine has energy. Energy cannot be created or destroyed. Where does it go? It's not going into how fast the chips are flying. Otherwise, they'd be punching holes in the wall. It's going into heating. And so these tools have to be able to handle high temperature and have all those properties I listed. And this is an issue because things like corrosion and adhesion and so on are actually usually promoted by high temperatures. And things also tend to get weaker at high temperatures. So this is the problem. So let's talk about the classes of tools. The first class is high-speed steels. high-speed steels. And everyone says HSS, which really doesn't save much because high speed and steel are all one-syllable words, so we're not really saving anything. A few types on the typewriter. So high-speed steels. The book, if I remember right, and if my notes are correct, says that 65% of the total value purchased. So high-speed steels, when the book was published, were about 65%. That has decreased. I would even suspect at this point, I don't have the numbers, but it's decreased. Even at that time, though, the amount of metal removed was only about 25%. So the tools represented 65% of the cost, but only 25% of the actual work. And why was this? Well, generally, high-speed steels are used for more complex tools. You don't use them for simple lathe tools. You use it for things like broaches, things like twist drills. You use it for complex geometries. Okay? The reason is these tools then don't remove as much metal, but we need these special shapes, and it's easier to make them out of high-speed steels than out of some of the other things we talk about. Okay, high-speed steel cuts soft materials well. So it cuts soft materials well. So you're in the plastics chapter. I've done a lot of machining in my life, never plastics, but I would suspect there's a lot of high-speed steels used there. We call it high speed because when it was invented, it was high speed. But it's the least speed of the common materials we have. So we cut the slowest. So if we're drilling a hole with a high-speed steel drill, we will generally run slower than we run with other tools. But it is tough. It's good for interrupted cutting. Interrupted cutting is when you cut, don't cut, cut, don't cut, something like that. Like if you have a cross hole that you're drilling through or something like that. It's good for old sloppy machines. It's where you need toughness, okay? So we come in two types for high-speed steels. We have T for tungsten or M for molybdenum. And you can tell that it's American, right? Because tungsten would be wolfram, W for the British, but we call it T for tungsten, or molybdenum. And there's all different grades. And so it's special steel, which have a lot of either tungsten or molybdenum. And then we usually add about maybe 4% chromium for hardenability, okay? Because we want it to be hard. Remember what I started to say. If you remember your steels, back when you were studying the materials, things like 4340 and 4140 have chromium in. They're easier to harden without distortion than like things like 1040. So it has chromium in. Probably will have some vanadium in to give more wear resistance, and maybe a cobalt to have a little bit hot hardness. But generally, when we have easy stuff to cut and we need a complex tool, we get it out of a high-speed steel, okay? Unless you buy really the cheap stuff, which is carbon steel, but we're not going to talk about that. Okay, I wanted to talk about, it's not mentioned in the book, but you're graduate students, so you should know it exists. There's a tool material called stellite, S-T-E-L-L-I-T-E. Stellite, S-T-E-L-L-I-T-E. And this is a cobalt chromium alloy and has good high wear resistance. And it is used for things like saw teeth, valve seats on engine valve seats, right? Good wear resistance is needed because that valve's popping up and down and hitting. Machine gun barrel liners, again, you're shooting a lot of bullets, so you need good wear resistance. That is sometimes used in lace, okay? And sometimes again in saws. Not that common, but I just wanted to mention it. The workhorse used to be high-speed steels, but the workhorse now of machining of tools is what we call carbides. And they're often called cemented carbides or sintered carbides. Cemented carbides or sintered carbides. So what these are is mainly tungsten carbide, little particles of tungsten carbide, micron sized, or maybe even down into submicron size. By micron size, I mean like 1, or maybe a little more, or maybe now into the submicron. Little particles of tungsten carbide. Remember, what did Edison make the light bulb of? Tungsten. Why? Because it can be really hot and it won't break. Okay, so tungsten is sort of the metal we use to take heat. And again, as I mentioned, you have heat. So tungsten carbide grains, but you have these little particles, and they're either, it's called cemented or sintered together, and really it's bonded by ductile metal. And usually this is cobalt, or some cobalt-based thing, as far as I understand. Okay, so I have a whole bunch of little particles cemented together by cobalt. Not a lot of cobalt, probably single digits, maybe in the upper level to single digits, maybe 10%, but probably maybe less, I don't know. Something like that. So it's particles that are together, and holding the particles together is some cobalt. Okay. This works fine for machining many, many types of things. But there's a problem with steel. The problem with steel is iron, I should say, not steel. The problem with iron is it's very carbon hungry. Steel likes to have carbon in it, right? That's why we had cast iron, which we talked about, higher carbon than the steels, which are the lower carbon. Okay? So if we use pure tungsten carbide, we tend to have a trouble that the carbon moves away into the steel you're cutting, and that's bad news. So what we call the pure tungsten carbide, we call straight carbides. We also have what are called complex or steel cutting carbides. And so complex or steel cutting carbides, and they have a combination. It's a complex, and it's not only complex as complicated, it's complex meaning it's some sort of chemical complex together. And it's tungsten carbide, which is WC, titanium carbide, which is T, lowercase ic, and tantalum carbide, TAC. T, lowercase a, is tantalum carbide. So these are all together. And so a common problem is that someone's trying to cut something with steel, it's trying to cut steel with a straight tungsten carbide grade, and they want to hurry up, so they're running very hot, and then they have a problem. They need to switch to a complex or steel cutting grade. Okay? Now, it's not a problem with cast irons. Okay? It's not a problem with cast irons because why? There's enough carbon in there, so the iron isn't trying to take carbon out of your tool. Not that it's going to matter, because we're going to find out later that the movement in cutting carbides is towards ceramics. Now, historically, we had these carbides, and that's what we had. And then we came up with coatings. And I think maybe your book talks about maybe 50-50, and that's what we had at about that time frame when I worked on it. It's now moved to more and more coated carbides. I'm just pulling a guess. I would say 90% or something is what we call coated carbides. So we put a coating on top of the carbide, okay? These coatings are done by the two manufacturing processes that we borrow from the electronics industry. The electronics industry has gotten very good at manufacturing. What do? How do we build electronics? We put layer and layer and layer and layer and layer on top. So we do the same thing with our tools. And the two methods are CVD and PVD. Okay? These are, and VD does not stand for venereal disease, it stands for vapor deposition. So we have chemical and physical vapor deposition. Okay? In chemical deposition, we bring two gases together and they react and form solid particles. Think of it as snowing, okay? You bring two chemicals together, they form solid particles, and they snow down on the surface and coat the tool, okay? These are not thick coatings, couple microns thick, okay? Historically, when we started with this, oh, I have coated tool, I have one layer, or if I have 2 layers, or I have 4 layers. Now, we stack layers like crazy, up to 50, okay? That's maybe the extreme, but something. So we stack the layers. So one way is chemical vapor deposition. The other way is physical vapor deposition. So in physical vapor deposition, let's say I want to coat this sheet of paper. This is my cutting tool. This is going to be my lathe tool. In physical vapor deposition, all this is in vacuum, even the chemical vapor deposition in vacuum. I'll have something here I want to coat, and I'll shoot ions up at it. Bam, 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 bam. And particles will float off and coat the surface. Okay, that's called physical vapor deposition. Okay? So what do we put on here? What we put on here is usually ceramics. Okay? So a common one is aluminum oxide, Al2O3. Okay? Sand essentially, right? Okay, we do different titanium ones, like titanium carbide, titanium nitride. Okay? These are not metal, they're covalent bonded things that we're putting on the surface. There's something called titanium carbonitride, which is a combination of titanium, carbon, and nitrogen. Okay, and we put all sorts of layers on top. Okay, so this is the way what is currently done, is we put layers. And I said bunch of layers, usually not the same thing. We may alternate maybe a little bit, but we put different layers for different reasons. And so one of the reasons is to stop diffusion, okay? One reason to stop diffusion. Another reason is to make a hard layer, right? Another reason might be to reduce friction when we're cutting the metal. So I think you can see what I'd want to do. You want your tungsten carbide tool, which is strong and has good heat tolerance, but you put a layer on top. So the friction, so the material goes off so you don't generate as much heat, a diffusion layer, and maybe also a harder layer actually, maybe on top of the diffusion layer. It depends. And so all your suppliers who think they have the best recipes, right, of the tools to use. And there's actually almost more money in the tools because what? They wear out, and you throw them out, than there is in the machines, believe it or not. Because if you're running a machine 24/7, cutting metal, cutting the hard metal, you're burning up tools. And there's a lot of money to be made. And so you hopefully will be the person either selling them, making lots of money, or the person buying them, saving lots of money. So it's important to do that selection. Now, since I was your age, which is a long time ago, everyone was saying, well, what do we need? We need to stand hardness, and we need to withstand heat. So we should have ceramics. And this is what people talk about. And ceramics are what? They're hard, they're inert, they don't react with anything, they're temperature tolerant, perfect stuff. Well, the problem is they can be brittle, okay? So that's the drawback. So what are the ceramics? Well, a common one is aluminum oxide, Al2O3, okay? There's other ones, you know. They're always predicted to take over. They're gradually taking over. Well, I don't know if I'd even say taking over, but they're becoming more and more popular. Okay, so one that's been quite successful is silicon nitride, Si3 and 4, right? If you remember, your valences, silicon is right under carbon, so it's 4. Nitrogen is to the side of carbon, so it's 3, so you need the reverse, Si3 and 4. Silicon nitride is popular for cast iron. Okay. It's hard, heat tolerant, and actually tough enough to cut cast iron. So that's one that's sort of become popular. Sometimes, again, we will do a cut. Let's say I want to reduce the diameter of this. The first rough piece that I have may have parts in the surface, hard parts, maybe some inclusions. I don't want something that's brittle. So I might cut the first layer off with a tungsten carbide of some kind, coated, well, nowadays coated, but coated or uncoated. Now, to get the final finished dimension, if I have to hold it real tight, I may cut it really fast, which will give me a smoother, nice surface. But since I've already smoothed it out, taken all the crap off the surface with the tungsten carbide, then I'll have a nice cut, and I'll go with my ceramic on top of it real fast, so it'll go quick. And I'll take a small layer, not a thick layer, because the thick layer is, you know, more chance of breaking something, my brittle ceramic. But for a finished cut, ceramics are pretty good. Okay, now, I had a project back in the dark ages of die casting dies, and so we had H13 steel. This is sort of an irrelevant, this is a side case, but I'll get to what I wanted to talk about in a second. H13 steel 44 Rockwell C. So it's hard, nasty stuff. Am I going to cut that? What I use to cut it is the hardest, second hardest thing known to mankind. What's the hardest thing? Diamond, right? Think of where diamond is. It's covalent bonding on your chart. What are on the two sides of carbon on the periodic Mendeleev chart? On one side is boron, on the other side is nitrogen. So if you cross those two together in a covalent bond, it's almost like diamond, right? And that's cubic boron nitride, okay? So instead of having carbon in that cubic structure, which is extremely hard, of course we don't, you know, graphite isn't hard because it's in a different structure. We have cubic boron nitride, okay? That's the hardest man-made material. It's expensive, okay? But if I need to cut something that's really hard, it's what I use. I said it was expensive. So what I used is I had a regular tungsten carbide, and I had someone take some of the top off and put on a thin layer of not real thin. We're not micron level. I don't even remember how thick it was, but it maybe a millimeter, maybe a half a millimeter, something like that, level on top. So cubic boron nitride is used to machine things like hardened die and mold steels, difficult steels and nickel alloys, okay? You don't have problem with the steel because, you know, there's no carbon there, right? It's boron and nitrogen, okay, in a tight covalent bond. So if you have the money, you can buy that. Of course, if you really have to cut hard stuff, then you use diamond. And we'll start first with polycrystalline diamond, PCD. PCD, polycrystalline diamond. Diamond is the hardest material. The only problem is it is carbon. Can't use it for steel. Nope, 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 nope. Unless you want your diamond tool to disappear. And if you've, you know, even when I bought my wife's engagement ring, diamonds were expensive, okay? We're doing a little better now because we can artificially make them. And actually, people in the MSc department here worked on that sort of thing years ago. So the loss of the diamond tool is not economically feasible. So you can't cut steel, and you have to watch really high temperatures, because then you can get oxidation, right? And changing diamond to carbon dioxide is a problem, not because of pollution, because you're not going to make that much carbon dioxide, but a cost. But it's very good for finishing cuts on non-ferrous metals. And I used this even when I was making lawn and garden equipment, right? On aluminum castings. It lasted forever. We still had the original tool when I left the company, right? I mean, eventually it will wear away. But for things, especially when we have aluminum alloys like engine blocks, which remember I said have silicon in the aluminum alloy, they tends to be abrasive. So if you use the diamond cutter, that's good. It leaves good tolerances and smooth surfaces. Okay, so that's the polycrystalline, where you have the crystals cemented together, and I don't even know what it is. Okay, there also is single crystal diamond. Okay. And the big thing that this was developed for was for the mirrors on making for space applications. Space applications and anti-ballistic missile things and stuff like that, where you needed really, really perfect, smooth, absolutely smooth surface. The rough cut you might do with something else, but then you go with a diamond right over the surface, really good. So that's sort of, I've gone up the hardness scale. I've started with high-speed steels, carbides, which are the workhorse these days, okay? We are getting better at making the carbides, so we make carbide drills, we make carbide milling tools, we do all these sort of things now. How can you tell whether your tool is a carbide or a steel? Tungsten is very, very heavy. So if you see two tools and one of them is more shiny, that's probably the steel one. But if you lift both of them and one's heavier, that's the tungsten one, okay? So we are seeing a lot more tungsten carbide, and again, for steel, I said it's a complex of titanium carbide and tantalum carbide, but it's mainly still tungsten carbide. We put enough of the other stuff so that the carbide's locked into it. So this is my understanding. Now, the next thing we need to talk about is tool failure. Tool failure. And there's two types of tool failure. There's breakage and wear. Now, when you're drilling a hole or milling or doing something and your tool breaks, it's a real problem. It's usually such a problem that it's not a problem. And how do I mean that? You'll make sure your tool isn't going to break. So then the question is it going to wear out? You want your tool to fare by wearing. So, you know, if I have a rough interrupted cut, I'm not going to use something that's real brittle, so it's not going to break. So the problem actually turns out to be tool wear. And that's a gradual degradation with use, okay? Where tool breakage is a sudden abrupt failure. I've broken tools, that happens, and you're not happy when that happens. But most of the time, you're in the wear region, and that's how your tool's going to wear out. Now, there's a trade-off between too aggressively and too conservatively. If you do too aggressively, the tool will wear out quickly. And there's two costs to this, and people sometimes forget the one. First of all, tools cost real money. So if you run too aggressively, they wear out, you spend an arm and a leg on tools. The other problem is, usually your machine is not working when you're changing the tool. So if the tool only lasts half a minute, you'll be spending all your time changing the tool, and you won't get any production done. So don't cut too aggressively. Of course, if you cut too slowly, you don't get the productivity. And this is also a problem. My general experience, and I visited a lot of plants in the United States, like I visited 6 plants for John Deere, 6 plants for Caterpillar, Ford, GM, small companies you never heard of. My experience is most of the time people don't want to spend money on tools, and they don't want to constantly be changing tools, so they run too conservatively and don't get enough productivity. This is a problem in the US. Our machines and our labor are not cheap. We need to be producing chips. And generally, you know, it depends on your local situation. Depends on your local situation. But I would say in general, we tend to run too conservatively. Historically, tools, especially the high okay? As a matter of fact, a guy I went to high school education worked for a company that made sharpeners. This has declined, but it still is a possibility, especially if you have an expensive high-speed steel tool. It still may make sense to sharpen it. Okay, so now, if you're awake in the back, I would like to use the overhead camera. Okay? So let's talk a little bit about the types of wear. So am I on the screen? Yeah. Okay, very good. Okay, so we're going to look at a tool. Let me see if I can get myself calibrated. Okay, here is my tool. And I'm going to say, I'm cutting, I'm going that way. So I'm peeling off a layer of material, peeling off a layer, right? And then, right? Okay. You see the blue there, that's my workpiece. And I'm peeling off a layer, and this, of course, would be called the chip with my tool. I'm moving like that. I'll give you a second to draw it. Okay, there's my tool. Now, on a knife, we'll have this angle in here will be very sharp, right? When you're cutting vegetables or fruit or something like that. We don't have a very sharp angle there because what? We're not cutting vegetables and fruit anymore. We're cutting tough stuff. So we need to have a big enough angle there. Okay, so I'll get the wear in 3 parts. The first part, which tends to be the most important, is what I call flank wear. And this will be where, by working like this, I'm now greatly exaggerating, I'll have that happen to my tool. What's black there disappeared from working. It started where, right here at the tip, that part wore away, so it wore back, and then it rubs on this surface, so eventually I get something like this worn away. That's called a flank wear, okay? And we measure that for flank wear width, okay? Flank wear width, or VB, which is the German, and I'm sorry, even though my parents spoke, I'm a Dummkopf and never learned any German, so I don't even know what those words are. But anyways, it's called VB, and people tend to use the German. So let's take a look at my tool. So now instead of a point, I have something that looks like that, sort of, greatly exaggerated. I've made the clearance angle really big so we can see. The flank wear width would be this width right here. Okay, so that's the flank wear width. The curve of this as a function of time is your standard wear curve that you see all the way, always. Okay, and so this is a wear. And this really applies to like a million things, not only to this. Initially, when you take something that's really, really sharp and use it, it'll wear a little bit at the start, pretty quickly. And then we have a more or less flat region, and then it all goes to hell, okay? That's sort of what you have here. It's what you have with bearings. I mean, this is the way life is usually. You have some initial wear, and then a small steady wear, and then all of a sudden it goes. Obviously, you want to change it somewhere like here, right? You know, that's the idea, okay? It increases because we start to get more and more friction on the surface, and on that bottom surface. On that bottom surface here, we get friction, and it just becomes a problem, okay? So that's it. Of course, this is where I do the regrind. I put the new surface maybe like this, right? And now I got a sharp point again, okay? So I can do the regrind on that and maybe be okay for a bit. Of course, nowadays it's almost better to just throw it away and have a new one, because regrinding it will cost you too much money in the US for labor and whatever. So that is an example of flank wear. Okay, one thing that can also happen is you lose tolerance. So you got to stay on top of this, because now the top surface will be up here, and you might lose tolerance a little. Now, in general, that angle is really shallow. The clearance angle in here, this clearance angle, we're usually talking single-digit degrees. 5, 6, 9, something like that. Very, very shallow in there. So it'll take a long time before that wear really causes you to lose tolerance, but something to think about. Now, you're going to learn in Chapter 8, before this material, you're going to learn, right? We're putting here a force and a velocity. Well, that is power. Where does that go? Right? It's a force and a velocity. Incidentally, there's a force in the vertical direction in my drawing, but is there any velocity? No. So I'm not losing power on that. Okay, I have to watch the force. The force may cause my tool, depending on the exact nature of the cut and the shape of the tool, the angles, and the edge will be rounded a little bit, whether it's pushing up or pulling down, probably pushing up in most cases. But there's no velocity, so there's no power loss. There is power loss, though, on the moving along the surface. That's heat. Where does it go? It happens in two spots, and you're going to learn this. One is the workpiece itself will shear in this zone here, right? The metal has to change. It's no longer, right? It's no longer like that. It's all of a sudden bent. And so it will shear in there. So that's where, you know, it depends greatly, but maybe half or maybe even less than half. So where is the other problem? The other problem is the friction on this surface. Remember, we're coating the tools to reduce the friction, among other things. The other thing is the friction on that surface. Okay. That is sort of bad news. Actually, both are bad news as far as the tool's concerned. The shearing will cause the chip to be hot, and then I'm rubbing a hot chip with a big force on the surface. And that will cause what is known as crater wear. Crater wear. And surprisingly, it's not hottest at the very tip, which you would think, which actually is good for us. Okay? It's not hottest at the very tip, but it's going to cause a problem in here. So let me redraw that. That one's too small here. Let me redraw a big tool. Big tool. Okay? And so my material, and I need to get my shear angle down a little bit. Okay? So here we go. That's my workpiece. So my tool is shearing, peeling off a layer. So well, I'm supposed to be drawing it separate. And then it'll eventually actually curl away. It'll lose contact. And then here's my, yeah, okay. Not too good a drawer. So the peak temperature will probably be somewhere in here. So I'm doing thermal bands. This is really hot in here. And those are the isotherms, right? Yeah, you're graduate students, you know this stuff. Isotherms, okay? Now, so what happens with the isotherms is it gets really hot in the center. And also, because you're really pushing, there's a big F, right? There's a big F there. So what happens? So because we're really pushing there, what happens is we get, this softens up, gets hot, softens up, and it wears away. So eventually my tool, instead of having that surface, maybe has that surface. And then maybe it wears some more and I have that surface. And now I'm in trouble because my tool will break off due to the crater. So I have to avoid crater wear because it can lead to breakage. Now, usually, and later on you'll get into the equations for that and so on, but that is a problem. Now, I want to, in order, because I only have 6 minutes left, maybe my watch is slow even. So I want to do, let's take a view, let's look, right? Let's look, right? Our view, oh man, that's a bad eye. Anyways, looking from that direction. Let's say I have a workpiece that looks like this. So again, blue is my work, and I want to peel a corner off. So my cutting tool, I'm going to make a hidden line here. I'm looking at this from looking this way. Now I'm cutting like this, okay? One of the things that can happen is I can get the third type of wear is what I call notch wear. And look at that workpiece. Where is the material going to most likely have contaminants, inclusions? Where is that material on that workpiece going to be the hardest because it cooled the fastest? The outside surface. So what will happen is, if I'm cutting like that, I might get a notch over there in the cutting tool. So it's not uncommon for me to get wear that would look like, whoops, I'm down off the bottom. Let me move it up. I get wear, if it's going to wear, it's going to wear like this, like this, like this, like that, right? Okay? The part on the right isn't going to wear because it's not cutting anything. The part in the center, or on the left, is cutting uniformly and nice, good material. The part that's cutting where the edge is may get a notch. And in reality, this is a problem for even if I'm cutting down the middle. If I'm cutting this one, you know, life's not fair. If I'm cutting that one, I'll probably get a wear that looks like okay, what's the flank width wear of that? Well, you know, draw a line somewhere to the middle and call it what it is, okay? Now, this all affects things. Remember here, I said this gets too hot. When does it get too hot? Well, when I'm dumping too much power in this region. So how do I dump power? Well, the force is going to be what it is, so maybe I have to reduce the V. If I reduce the V, it also gives more time for the heat to move away. Okay? It also depends what my work is. Aluminum conducts the heat like crazy. If you have good tungsten carbide cutting tools now, I find it hard to cut too fast because you can go to town because it's real good. What's the problem with titanium? I told you this earlier. The problem with titanium is there's no thermal diffusivity. The heat does not go into the chip or the workpiece. The heat just sits there and softens your cutting tool. And this is why it's so difficult to manufacture with titanium. Not that it's strong, because steels are stronger, and like even aluminum alloy, well, 7075 T6 is quite strong, but you know, the problem is, again, the problem is the heat, getting the heat and this. And so the tolerance sort of goes in the way I said. You know, diamond, really, you don't want it so hot. But the others, it pretty much goes in the direction I talked about them. So that's why you can cut faster with them. Not only are they harder, they have better hot hardness. Okay? On Wednesday, Dr. Greenslet will be back, and we'll go back to where you're supposed to be. I'll tell her about this. You're responsible for this in this section of the homework book, but it's a nice thing by itself. Thank you. Have a good week. Cut.